Well, welcome to second quarter. And second quarter, we're going to be starting off with the chemistry of life. And the first section, section 2-1, the nature of matter, is basically a review of things that you've already learned in physical science. So we're not going to spend a lot of time actually going over all of these because you should already know them from physical science. So we'll start out with dog's thirsty. So we'll start out with atoms. An atom is the basic unit of matter, and an atom is made up of 3 subatomic particles, and those would be protons, which carry a positive charge, neutrons, which have no charge at all, and electrons, which carry a negative charge. As you know, the nucleus, which is at the center of the atom, contains both protons and neutrons. The electrons are in constant motion in the space surrounding the nucleus, and sometimes this is referred to as the electron cloud. Atoms are neutral because the subatomic particles have equal but opposite charges, which means that the charge inside the nucleus usually balances the charge outside the nucleus. Elements. No, we are not going to spend a lot of time going over the periodic table. In biology, we assume that you already have learned this in physical science. So we're just going to kind of review because we focus on specific elements just in biology. So an element is a pure substance that consists entirely of just one type of atom. More than 100 elements are known. I don't know what the number is up to date, but I know there's at least 112 or 113. Only 24 are commonly found in living organisms. And if you recall from physical science, elements are represented by a 1 or 2 letter symbol. So let's see if you can remember. H is for hydrogen, C is for carbon, Na for sodium, and so on. So a lot of times now in the future, I'm going to just abbreviate certain things using their symbols. I know that you have seen this before, so we're going to go through it kind of quickly. If we were looking at an element in the periodic table, and by the way, your book in the very back has a periodic table that you may want to refer to for some assignments. So the very top number that you're going to find in one of those little squares for the elements is the atomic number. The next one is going to be the element symbol. Then, of course, the element itself, and finally, the atomic mass. Now, in order to make some of these calculations better, some of the things that you might want to remember is that the number of protons in an atom of an element is the same thing as the atomic number. So this number 6 equals the number of protons. And once again, we said protons were located where? That's right, in the nucleus. And they contain what kind of charge? That's right, a positive charge. Isotope is an atom of the same element, but differs in the number of neutrons they contain. And if you remember, neutrons have no charge, so they have no charge, and they are also found in the nucleus. The sum of the protons and neutrons in the nucleus of an atom is its mass number. So, in other words, its atomic mass. So protons plus neutrons equals atomic mass. That's very important that you remember that. And remember, both protons and neutrons, once again, are in the nucleus. The weighted average of the masses of an element's isotope is called its atomic mass. The number of electrons does not change when we're talking about an isotope. So all the chemical properties stay the same. So once again, the number of electrons, which are in the cloud outside of the nucleus, does not change. And the number of electrons also equals the number of, what was that? Protons. Correct. So if we're talking about an isotope of carbon, and carbon is one of the elements that we refer to all of the time in biology because all living things are made of carbon, isotopes are identified by their mass number. Remember, their mass number equals protons plus neutrons. So here are three different isotopes of carbon. We have carbon 12, which is the carbon that we're most familiar with when we're working in chemistry. It's not radioactive. Carbon 13, non-radioactive, and carbon 14, radioactive. We're going to talk about the significance of this radioactive carbon 14. Once again, in isotopes, you will notice down here, the electrons and the protons stay the same in all three of these isotopes of carbon. What changes is the neutrons. And remember, the neutrons are in the nucleus. So, radioactive isotopes, they have what's called an unstable nuclei that break down over a constant rate of time. And a lot of times what we use these for is to do what's called carbon dating. Radiation given off can be both dangerous and have practical uses. So, what do we use radioactive isotopes for? We use those to determine the ages of rocks and fossils. We use radioisotopes to treat cancer. If you've ever heard of anyone having radiation, that would be where we use radioactive isotopes for. We kill bacteria that spoil food. A lot of times the meat that you buy in the grocery store, especially the ground beef, has been zapped to kill the bacteria so that there aren't any additional bacteria in your ground beef. And tracers that follow the movements of substances within organisms. So sometimes if you're going in to have an x-ray, they might have you drink something, or they may give it to you in an IV, and then when they're actually looking at your body, they can follow these things because they've given you what's called a tracer to follow. So those would be 4 ways that we use radioactive isotopes. Chemical compounds. A chemical compound is a substance formed by the chemical combination of 2 or more elements in definite proportions. A chemical formula is used to illustrate the composition of these compounds. And you worked with a lot of chemical formulas when you were doing physical science. We are not going to use a lot of them in biology, but I just need to review these facts or this information with you. An example of a chemical formula would be water. An easy one. Water contains 2 atoms of hydrogen for each atom of oxygen. So its chemical formula is H2O. Once again, it has 2, and we've got that little subscript down there. That means that there are 2 atoms of hydrogen. And then we've got 1 atom of oxygen right here. So that's why water is H2O. the physical and chemical properties of a compound are usually very different from those of the elements from which it's formed. And your example is going to be, once again, water. Hydrogen and oxygen are both gases at room temperature. When they combine explosively, they form liquid water. Little mole man is cute, isn't he? All right, chemical bonds. That's Mrs. Worm calling. She wants to know where we're going for dinner. We'll silence her for a minute and finish our little lecture here. The atoms and compounds are held together by what are called chemical bonds. Mrs. Worm? I'm going to call you back because I'm in the middle of giving my podcast. And I'll call you in 2 seconds. Okay, bye. See? That was a quick call. All right. Back to the different types of chemical bonds. The two types are going to be ionic bonds and covalent bonds. You remember these from physical science. In ionic bonds, they are formed when one or more electrons are transferred from one atom to another. So once again, in an ionic bond, they are transferred from one atom to another. The second type of bond is a covalent bond. And in a covalent bond, they are shared. So once again, ionic is transferred, covalent is shared, when the electrons are shared between atoms. An ion is a positively or negatively charged atom. And you have seen these before. Oppositely charged ions have a very strong attraction to one another, and you put these together when you were making chemical compounds in physical science. When atoms share 2 electrons, that is a single covalent bond. So if you look at carbon over here, it's got 1, 2, 3, 4. Each of those are single bonds. 4 electrons shared gives us a double bond. So you can see right here, there are 4. 1, 2, 3, 4 electrons that are sharing. That gives us a double bond. 6 electrons shared gives us a triple bond. And here would be an example of your triple bond right here. The structure that results when atoms are joined together by covalent bonds is called a molecule. And the definition of a molecule is the smallest unit of most compounds. So you have to remember the difference between a compound and a molecule. An example, water is a molecule with each hydrogen atom forming a single covalent bond with the oxygen atom. So here would be an example of a water molecule. If we were to write that out, there would be O, and then an H, and then an H. Sometimes it's written like this, and it's called the Mickey Mouse molecule because it looks like Mickey Mouse. All right, that concludes section 2-1.